Welcome folks, we are going to show you a bandpass filter example using op-amps. In this circuit we are asking you to find the transfer function that is V out of S over Vs of S. By looking into the circuit we can see that the input signal Vs is connected to a 50 microfarad capacitance, we called it C1, which is also connected to a 1 kilo ohm resistance that is called R1. And the resistance is connected to the feedback path, which has R2 in parallel with C2, where R2 is 20 kilo ohm resistance and C2 is 50 nanofarads, which is connected to the output of the op-amp. And of course, at the output of the op-amp, we have the load resistance, and here we have a 10 kilo ohm. Because the non-inverting input is grounded, this amplifier becomes inverting amplifier. And we know that the gain of this amplifier is going to be negative Z2 over Z1. And to calculate the gain of the amplifier, the first thing we have to do is to find the impedance of the capacitances C1 and C2. So the capacitor C1, when you convert it to the impedance Z of C1, that will basically equals to 1 over S C1. And the capacitance C2, when you convert it to Z of C2, that is basically going to be 1 over SC2. Now, we can state that the transfer function is basically H of S, that is will equal to negative Z2 over Z1. And we know that Z1, which is the input impedance, is basically R1 plus Z of C1, and that is because the resistor R1 and the capacitance C1 are in series. Then basically the equivalent impedance of that is to add them up. Now we know that R1 is going to be the same, and we already calculated ZC1 to be 1 over SC1. We would like to express this impedance as a rational function, so we're going to multiply the top by SC1, and that is basically to get the common denominator. So what we're going to have is S times C1 times R1 plus 1 over S times C1. We like to write it in this form because usually we like to represent the transfer function as a rational function. And to do that, we like to simplify the impedances also as rational functions. The next thing we're going to do is we're going to evaluate Z2. And Z2 is basically the parallel impedances of R2 and C2. So we can state that Z2 is basically R2 in parallel with Z of C2. For two impedances, the parallel equivalent impedance is going to be the product over the sum, which is R2 times ZC2 over R2 plus ZC2. What we're going to do next is we're going to substitute for Z2, which is 1 over SC2, into this equation. So what we will end up having is that R2 over SC2, that is simply the product over the sum, which is R2 plus 1 over SC2. Just like we did with Z1, we would like to express Z2 as a rational function, and to do that we are going to multiply the top part and the bottom part by SC2, and when we do that we will end up at the top with R2, and at the bottom we're going to have SC2 times R2 plus 1. As we stated earlier, the transfer function H of S will equal to negative Z2 over Z1. So we can say that this is equal to negative the values of Z2 going to be R2 over SC2 times R2 plus 1, and the values for Z1 going to be S times C1 times R1 plus 1 over SC1. As we stated earlier, we would like to express the transfer function as a rational function. So we need to simplify this form. And the way to do that is I'm going to bring the denominator of the top part to the bottom. and the denominator of the bottom part to the top. So basically, I'm going to multiply by SC1 to the top. So this will equal to minus SC1 times R2. And I'm going to bring the denominator of the top part to the bottom. So what I will end up having is 1 plus SC1 times R1 multiplied by 1 plus SC2 R2, which is the denominator of the top part. Now all what I have to do is just plug in the values of the R's and the C's. What I will end up with is that the transfer function h of s will equal to negative s over 1 plus s over 20 times 1 plus s over 1000. So this is the transfer function, and it is a friendly function that we can deal with very easily. In fact, that we can predict the frequency response of this circuit. So if we plot a rough estimate of the frequency response, for that this will give you a plus 20 dB per decade until you hit the first corner frequency, and that is at 20 radian per second. Then it will flatten out until you hit the 1000 radian per second, and then it will start to drop at a rate of negative 20 dB per decade. So by looking into the frequency response, clearly that this is a bandpass filter, because this particular circuit will only pass frequencies within the bandwidth of 20 radian per second to 1000 radian per second. Now keep in mind that this frequencies are in radian per second. When you convert it to hertz, the 20 radian per second roughly going to be 3.2 hertz, and the 1000 radian per second roughly going to be around 160 hertz. It is worth mentioning that the gain at the sharp edges or the corner frequencies is actually 3 dB below the mid frequency gain. So the gain at the 20 radian per second and at 1000 radian per second going to be roughly 70% of the gain in the mid frequency gain. We use the mid frequency gain here because that is the highest gain, since this is a bandpass filter. What we are going to do next is we are going to show you a computer simulation using OrCAD PSpice software. We have the circuit built in already. If we look into the schematics in OrCAD, we can see that we have over here the op-amp circuit, and this op-amp circuit has the 1 kilo ohm resistance connected to the 50 microfarad, which are connected to the input voltage source, that is AC voltage source. The feedback loop going to have R2 and C2, which are the 20K in parallel with the 50 nanofarad. That is connected to the output of the op-amp, and at the output of the op-amp we have a 10 kilo ohm resistance. We already decided to do an AC sweep, so if we look into the AC sweep, we're gonna do AC sweep from 0.1 hertz to 10,000 hertz, and we're gonna use the resolution of 1000 points per decade. Now keep in mind that our circuit has a corner frequency at 20 radian per second. When you convert that to hertz, this basically going to give us roughly around 3.2 hertz, and the other corner frequency is at 1000 radian per second, and when we convert it into hertz, that's roughly going to be around 160 hertz. So let's go ahead and run the simulation, and when we run the simulation, so clearly that this will look like a bandpass filter, where we have the highest gain is between the bandwidth of roughly around 3 hertz and roughly around 160 hertz. Now keep in mind that over here we are plotting the gain in volts, so I'm going to convert that to dB. So to do that, I'm going to come into the graph and I'm going to double click on it, and then I'm going to convert the output voltage to dB, and keep in mind that this is the gain since the input signal value was assigned to be 1 volt. So whatever the output going to read, that is basically the gain. So this is a tricky way of evaluating the gain right away by assigning the input voltage to be 1 volt. So we're going to convert it to dB. So I'm going to write dB open bracket, and then I'm going to add the component of the output voltage, and then we're going to click on the dB, and that is basically what we have in dB. The slope of the line here is going to be 10 dB per decade, and then at the frequency of roughly 3.2, you're going to have 3 dB below the gain of the mid frequency, and then around 160, we're going to also have 3 dB below the mid frequency gain. Clearly, this is a bandpass filter where the frequency between 3 Hertz and 160 Hertz has the highest gain. And as we leave this range, then the gain will drop dramatically at a rate of 20 dB per decade. So I have shown you a bandpass filter example using op amps. Thank you so much. I hope you like this example.